Today's lesson is 11.2, Strong and Weak Acids and Bases. Today we're going to finish up Unit 3, and we're going to cover 11.2 and 11.3 this evening. So, strong acids. An acid that dissociates completely into ions in water is called a strong acid. So an example of a strong acid is here, as we have hydrochloric acid. There's a list of strong, weak acids that you will see throughout this lesson. Clearly, you're not going to have to memorize any of the strong acids. But anyhow, what this means, right, is that they dissociate completely into ions, which means that every HCl molecule that we have in water, it will dissociate into its respective cations and anions, okay, in water. So 100% of it will do this, okay? So if that is true, then that means if I had 1 mole of hydrochloric acid, then all 1.0 moles per liter will contain either the hydronium ion, if you want to look at it as the hydronium ion, right? If we're referring to this, we're referring to Bronsted-Lowry. If we're writing it down as this, we're referring to Arrhenius' theory. It doesn't really matter which one you use. It is fine with me. Weak acids, on the other hand, only dissociate slightly, okay? So really, they will only dissociate about 1% of the time. And that, an example of a weak acid, acetic acid found in vinegar, okay? Which means if I had, let's say, 100 molecules of acetic acid, okay? If I had 100 molecules of acetic acid in water, only 1 will dissociate into this, okay, the acetate polyatomic and our proton using Arrhenius' theory, which will leave a remaining 99 of them to remain intact as a whole acetic acid molecule. Okay, so that's what this means, this weak acid, strong acid, that if I had, let's say 100, right, to demonstrate the 1%, I'd have 100 of them and 99 of them will stay as is in water, and only 1 will actually break apart into their respective ions. While strong acids, on the other hand, every single one, right, if I've got 100 of them, I put in 100 molecules of HCl, all 100 of them will dissociate into their anion and cation. So here's just a comparison, a diagram I found online of that hydrochloric acid. If you look closely, okay, if you look closely at this one, you'll see that everything has been separated. Okay, so the hydronium ion is going to be this molecule here in red. The green represents the chloride. Okay, so notice that none of them are intact as one whole. However, when we're looking at the acetic acid, and be aware, there are different ways you can write the acetic acid. I wrote it, the diagram wrote it this way. Up here, I wrote it that way. It's the same thing, no different. Anyhow, if you look at it, here is the hydronium ion, or the hydrogen, the proton, if we were looking at Arrhenius theory. But notice how everything else, right? Look at how many remain as whole acetic acid molecules. Okay, so that dissociation only happened here that one time in this diagram. Okay, so that's what we mean by a weak acid. So a weak acid will not dissociate into their respective ions like strong acids will. So we've got different types of protic acids. And these protic acids represent how many protons can actually, in fact, dissociate. Okay, so monoprotic acids are just acids that contain one H in their formula. Okay, so here are some examples: hydrochloric acid, hydrobromic acid, hydroiodic acid. These are all the binary acids that we talked about back in chapter 4, right back in unit 1. So, which means right here, HCl, right, 1H, H hydrobromic acid, right, HBr, let's say another one here, hydrofluoric acid. Here, all of them contain just one H in their formula, and hence the reason why they're called monoprotic acids, because there's only one proton that will dissociate and bind to water if you're looking at Bronsted-Lowry or Arrhenius. Okay. So diprotic acid, you can almost assume that di meaning two proton acids. So if you look at the any acid that contains two H's in their formula, here's an example. Sulfuric acid is a diprotic acid because there are two H's. Another one is hydrosulfuric acid. Okay, there's two H's that I can dissociate. But understand this, sulfuric acid is a very strong acid, and so it dissociates 100%. However, that 100% dissociation only occurs for the first proton. The proton that's left here can further undergo a additional dissociation, but this is in fact considered a weak dissociation. Okay, so that first dissociation is always the strongest. So the first dissociation is the strongest. Any other dissociation of a secondary proton or even a tertiary proton, a third proton, is considered weaker than the first. Okay, and sometimes you will see this reversible arrows, which means that as it dissociates, it reassociates back to allow another molecule to do that. Okay, so that's all it does. That's what that means. It just it goes like a back and forth, a reversibility reaction. Okay, that as we go in this direction, it will also go in the opposite direction. Okay, while the single arrow, as you see up here, okay, only goes in one direction. Okay, and lastly, triprotic acids. Triprotic acids, we've got 3 protons as we have here with phosphoric acid, and the same thing here. The difference here, though, because it is a slightly weaker acid, it will dissociate and go back and forth. Okay, so notice that we're going to have the first dissociation. This is going to be the strongest of the dissociations. And then this here will further dissociate down here. Okay, to give off another proton. This will has the ability to give off another proton. But again, the strength in terms of this dissociation, the strongest is in the first, not as strong in the second, and definitely the weakest would be in the third. So when we have these strong and weak acids, we also have strong and weak bases, and they follow the same premise of acids where they dissociate 100% of the time. Okay, so that 100% of the time means that, well, here's a strong base. It means that they will dissociate. The sodiums and the hydroxides will come apart in water 100% of the times. In a weak base, the OH will dissociate 1% of the time, or approximately 1% of the time. All the rest kind of goes. Most bases are considered weak. Okay, so therefore they slightly will dissociate. But understand that some, like sodium hydroxide is considered a very strong base. Okay, let's get to the tail end of 11.2, looking at the power of the hydrogen, what is referred to as the pH value. So here we have, at the bottom, a Bronsted-Lowry acid-base equation. So we know that water can actually act as an acid or as a base. So let's assume this water is the acid, and which means that this will be the base. So according to, and so it's just a review from 11.1, Bronsted and Laurie said that acids, if something is an acid, it will give up a proton to the base. And a base is something that will accept the proton. And in return, the part that becomes, the part that becomes the hydronium ion becomes what is referred to as the conjugate, conjugate acid, while the one that has lost the proton becomes the conjugate base. So that's just a recap from 11.1. So in terms of water can act as an acid or base. But the fact that what this example is also trying to lead is the fact that we've got an equal collection of so-called things that make something an acid and a base. Hence the reason why water itself has a pH value that is equal to 7. And 7 is considered a neutral value for pH. So on that scale from 0 to 14, 7 being right in the middle, meaning completely neutral. So pure water is considered neutral. Again, whatever other substances mix in with water can make it slightly acidic or slightly basic. Right? If we think about rain is considered acidic, even though yes, it is water, but it is mixed with other things. It's not pure water. Anyhow, on average, at 25 degrees Celsius, about 2 water molecules in a billion actually will dissociate as such. Okay, so if we have an equal value of hydronium ions as we do with hydroxide ions, we will have a molarity or a concentration of this acid base at 1 times 10 to the power of -7. But don't worry about memorizing any of these values because these are values that we can actually calculate. So, and this is where we're going to, I'm going to kind of skip through some of this, go through it a little bit quickly, just because it's not what the math isn't really that I worry too much about. It's how to calculate that where I want to focus on. Okay, so anyhow, a few things here. We've got this Danish biochemist by the name of Søren Sørensen who came up with this logarithmic value, numerical value for calculating the pH scale. And logarithms are values of powers of 10. Okay, we're not going to worry about these powers of 10. I'm not going to question you, but just a really quick math lesson here. So the logarithm of 10 is, so what you want to look at is 10 to the power of what will give me 10. So the power, 10 to the power of 1, okay, 10 to the power of 1 is going to give me a value of 10, which means that the logarithm of 10 is 1. The logarithm of 100 is, again, same thing. 10 to the power of what is going to give me 100. And so that x value is 2. So that means the logarithm of 100 is 2. But that's just really quick, simplified version of what is a logarithm. What I want you to worry about is the following, not this one, but this is just a scale of our pH values, like really strong acids, really strong bases, and notice here, pure water. But anyhow, moving on, this is what I want you to know. I want you to know the equation to calculate the pH is equal to negative log, and in here, this H plus is what you're going to put. You're going to put your concentration value. Okay, so this is going to be whatever your moles per liter is, which means, hint, hint, you might have to calculate this ahead of time to substitute it in to find the pH value. Okay, please test these questions out with your specific calculator, because from calculator to calculator, the process varies. Okay, some calculators allow you to just type this in as is. Some calculators, on the other hand, require you to do the reverse. So please make sure you know how to substitute these and get the correct value. Hence the reason why I practice the sample problems, do the homework questions, make sure your answers on the calculator get the answers that I provide for you in my answer keys. So again, that H plus could be H plus, or it could be the hydronium ion. It doesn't really matter what value you use. But anyhow, so understand that the pH value, there is no unit. So pH is equal to 7. pH is equal to 2.5. There's no set of units after that number. Now, to do the reverse of the pH value, so sometimes you might be given the pH and being asked, okay, calculate the concentration. Okay, so these square brackets represent concentration values. So to find, let's say, the concentration of the hydronium ion, you take 10 to the power of a negative pH. Okay, so if we wanted to, if we had a pH value of 6.5, right, you substitute 10, okay, you punch in 10 in your calculator to the negative 6.5, hit equals to give you your value. And remember that whatever value that is, that answer is going to be in moles per liter. Okay, so some sample problems here at the end for you to practice. Okay, so all it is really is substituting this into this equation. pH is equal to negative log, and here 3.8 times 10 to the negative 3. Okay, throw that in, find the answer, again round to the correct number of significant digits. For questions 3 and 4, on the other hand, 10 to the power of that negative pH and just hit equal, but remember that whatever that value is, it's in moles per liter. Okay, so practice those questions. Not much really to take up in terms of that, but again, make sure that your values equal my values that you'll see on these slides. Okay, so here are the answers. But again, please test these out. Don't assume that you know how to do them. And then there's some more here. So with regards to these sample problems here, if you're given the pH, again, use the formula from pH to find the concentration. If you're given the concentration, use the value to find the formula to find the pH. In terms of this part, what you're filling out is just identifying based on whatever values we have here. Is it an acid, base, or neutral? Acids, so acids have a value smaller than 7. Okay, bases have a value that is greater than 7. Okay, so just with these values here, this is a basic solution, this is an acidic solution, this is also an acidic solution. So on this side here, in terms of the effects of litmus paper, in 11.1, we talked about how does it, if we put litmus paper into an acid, if we put litmus paper into a base, what are the color changes? And anything that is basic will change blue. Anything that is acidic will change red. Okay, and then of course find the rest. But the answers can be found at the end of the slides. Okay. I hope you liked this video. If you did, do not be shy to hit that thumbs up button. And while you're clicking the thumbs up, click on that subscribe to stay tuned to my new videos. Thanks for watching.